Hello my dear students. In this video we will be looking at some properties of the unit tangent vector, and I want to let you know that in the last two videos the numbering was wrong little bit, right? So it was by mistake written video 9 but it is 10 and 11. Okay, I'm sorry for the confusion. Okay, but in the title the name is correct, but when you open it while I am recording the video number is written as 9 in the last three videos. Okay, so you read it as 9, 10 and 11. Okay, anyways, so in this video we are going to look at the properties of tangent vector, and in the next video we will see that these properties will lead to a very important definition which we need physically also again and again for any kind of motion study, right? If motion of a particle we have to study, then we need these definitions. So anyways, first of all, in this video it's plain simple. We have to just look at some properties. So I am writing here, assume that, so what are the properties? So we are writing, assume that the path x always has non-zero speed, This is only for everything to make sense, because tt will make sense because the unit tangent vector is defined as x prime t upon x prime t modulus. It will make sense only when xt is never 0. X prime t is never 0, has non-zero speed. That means x prime t is never 0. Okay, modulus. Okay, fine. Okay, then we have the first property which says that dt over t, rate of change of t with respect to t, is perpendicular to t vector for all t. Okay, this is the first property. Okay, so we can just prove it. It's very simple. tt is a unit vector, right? So if you take the dot product of tt with respect to itself, that would be 1, because that means the modulus of tt is 1. So dot product is basically modulus of this vector times modulus of this vector, cos of the angle between them, which is 0. So that is 1, right? So we get that tt is a unit vector. Therefore, we have modulus of tt equal to 1, and that gives us the dot product of tt with itself is also 1. So now if I differentiate with respect to time, so you'll get dy by dt of tt dot product with tt equal to derivative of 1, which is 0. So you get, now use product rule here. So if we use product rule, this is going to be tt dt by dt dot product plus dt by dt times tt dot product equal to 0. So you get 2 times t dot dt by dt equal to 0. That gives you t dot dt by dt equal to 0. So that gives you t and dt by dt are perpendicular vectors. Okay, so this is an important result. So if you try to visualize what we are saying, this is t vector, right? Okay, so this is your t vector. Later on you are going to use it, right? So this is your t vector which is tangent along at any point. This is a tangent, right? This is my t vector. So what I am claiming is that this vector dt by dt is a perpendicular vector. Okay, so this is what we are claiming, and we will look at the physical interpretation of all these things in the coming videos, right? Okay, so this was the first property, and this was very simple to prove. Now there is a second property which is a little difficult to prove, but it's okay. So now we are concerned about this vector here, dt by dt. So we are saying that at any point t equal to t naught, or any point, the modulus of this vector tells us is equal to the angular rate of change, the angular rate of change of direction of t, okay, with respect to small t, right? So what we are saying, suppose you have your curve, at this point you have some tangent vector. When the point changes, the tangent vector also changes. So angular rate of change of the direction of t. So direction is changing, right? So there is some rate, angular rate of change of the direction of the unit tangent vector, and we are saying that is equal to this. At a point t naught, the angular rate of change of the unit tangent vector is equal to this. So this is the rate at which the direction is changing. Now you can see that this quantity, that rate of change of the direction, can be, of importance in many physical situations. So this is what we are going to do now, right? Okay, so if you look at point t, suppose this is my tangent vector, okay, at point t naught, and then after some point del t, tangent vector changes. Suppose this is my tangent vector, okay, so we can always make them coincide, like tails we can join. Then this is going to be del t vector, right? And this is your del theta. Then angular rate of change of t is, you can see, that is del t by del t, del theta by del t, limit del t going to 0 from positive side, because we are taking del t to be increased. Like we are going to increase t naught to t naught plus del t. That means del t is positive. Does that make sense? So this is the quantity we are looking for, and we have to prove that this quantity is actually equal to this quantity, right? Okay, so for that we need some manipulations. So first of all, I'll look at this triangle and apply cosine law in this triangle. So what is cosine law? You all know that cosine law is, if I have, this is my A, B, C, this is angle theta, then we know that, okay, let us just keep, this is angle C, this is angle A, this is angle B. Then we know that, you know that what is the sine law? Sine law says that C square is equal to A square plus B square minus 2AB cosine of C. Okay, so this is the cosine law. Now try to apply it here. So that says the magnitude of this side, that will be mod of del t square, equal to magnitude of this side square plus magnitude of this side square. So that would be, let us just, because we are not going to dimension higher than 3, so we will keep it like this. Del t modulus square equal to, this is your C square, equal to A square, that will be t at t naught modulus square plus t at t naught plus del t modulus square minus 2ab, okay, modulus of t naught plus del t, and then cos of the angle between them, cos of del theta, right? So now what is this modulus? This is, because t is a unit vector, therefore its modulus is always 1. So this is 1 square plus, this is also 1 square minus 2, this is also 1 del t, and then this is also 1 cos of del theta. So you get del t square modulus, okay, so we get that del t square modulus is square root of 2 minus 2 cos of del theta. Okay, so from here, if I try to look at del theta upon del t modulus, okay, limit del t going to 0 from positive side, so that would be limit del t going to 0 from, now I why I am taking this, because I want to bring something like this here, okay, here. but first I am taking capital T here, then we'll convert it into small t using chain rule. So this will be del theta, and we just calculated this factor in terms of theta. Here it is 2 minus 2 cos of theta, del theta. Now this is limit del t going to 0 from positive side, right, and this is equal to del t going to 0 from positive side. This is del theta upon, you can take 2 outside, so 1 minus cos of del theta. Now you can use your trigonometry information. So this is going to be, this is the 1 minus cos 2 theta formula. So this is del theta upon 2 sine square del theta by 2 square root limit del t going to 0 from positive side. So this is going to be limit del t going to 0 from positive side del theta upon 2 sine of del theta by 2. So this is equal to limit del t going to 0 from positive side 1 upon sine del theta by 2 divided by del theta by 2. Now as del t goes to 0, del theta also goes to 0. So this becomes limit del theta goes to 0, 1 upon sine del theta by 2, del theta by 2, this is 1. Right? Okay, so we get that. Therefore, we get that this quantity limit del t going to 0 from positive side del theta upon modulus of del t is 1. Okay, so this is what we got. Right? Now we are looking for this quantity here. Right? We want with respect to time. So now we are looking for del theta by del t limit del t going to 0 from positive side. So this would be equal to limit del t going to 0 from positive side. I am introducing this del theta upon modulus of del t upon del t. Now what is this quantity? We just calculated that this quantity is 1. So this is 1 times limit of del t going to 0 from positive side del t upon del t. So this is equal to 1 limit del t going to 0, because del t is positive, so I can take it inside the modulus. So what is this? This is nothing but dt by dt. So what we get? We get that limit del theta by del t going to 0 is equal to dt by dt modulus. Okay, this is modulus. So therefore, the modulus of the rate of change of the unit tangent vector with respect to time represents the angular rate of change of t. Angular rate of change of t, that means the direction of the unit tangent vector, okay, with respect to t. Okay, angular rate of change of direction of t. Does that make sense? Right? So we will see that this is a very important result which will lead us to the definition of curvature, which we are going to discuss in the next video. Thank you for watching this video. Please share this video and subscribe to our channel. And if you have any comments or doubts, please write in the comment box. Happy learning.